Welcome to Chemi tutorial channel. Today we are going to discuss the chemical reactions of phenols. So first of all, in these reactions we will discuss the acidic character of the phenols. We know that phenols, they are acidic in nature. This is phenol. So first of all we are taking acidic character. As we know that phenols are acidic in character, they react with very active metals like sodium and also with strong bases like sodium hydroxide. And the reaction is given like this. This is reactive metal sodium. When phenol reacts with sodium, the product formed is a salt, that is sodium phenoxide, and hydrogen is released. The reaction seems to be very similar to the reaction of metal with acid. Metals also react with acids to give salt and hydrogen. Same reaction is here. So we can say that they are quite acidic in nature. So we can see here, I balance the equation, and their acidic character is so pronounced that they can also change the color of the litmus from blue to red. Because they are quite acidic in nature, they also react with bases. Now we can write the reaction of the phenol with a strong base like sodium hydroxide. So it will be similar to acid-base neutralization reaction. Again the products will be salt and water here. So the salt formed is same. It will be sodium phenoxide plus water is formed in this reaction. So this is similar to acid-base neutralization reaction. Now we can compare the acidic strength of the alcohols and phenols. Now let us compare the strength of the alcohols and phenols. So now we are comparing comparison of acidic strength of alcohols and phenols. So we will compare the acidic strength of the alcohols and phenols basically in 3 points. The first point that we are going to discuss is the plus I effect of the R group in alcohols, and on the other hand there is benzene ring in the phenol which withdraws electron density. So the effect is opposite to each other. You can see here, in general we can write alcohol as this. We know that this alkyl group present in the alcohols is electron releasing in nature, but in case of phenols we can see that this benzene ring present, it is electron withdrawing. It can withdraw the electron density from oxygen towards itself. So what will happen in case of alcohols? When electrons are released towards oxygen, then OH bond is strengthened. So the release of proton is not easy in case of alcohols. But in case of phenols, as the electron density is withdrawn by the benzene ring, so what will happen? This will lead to the easy release of a proton, that is H positive ion. So here in the alcohols plus I effect is there, but here electron withdrawing nature of benzene ring is there. So the effect is opposite to each other. So that's why phenols are more acidic than alcohols. Second point, we can say that in case of alcohols, if I write alcohol like this, I can see that the carbon to which hydroxy group is attached is sp3 hybridized. But in case of phenols, the carbon to which hydroxy group is attached or hydroxyl group is attached, this carbon is sp2 hybridized. sp2 carbon is more electron withdrawing, it is more electron active as compared to sp3 hybridized carbon. So again, if it withdraws electron density from oxygen, then there will be easy release of proton here from here, and here there will be little bit less tendency to release proton. So again, the second point we can discuss the hybridization of the carbon to which hydroxyl group is attached in both the cases. Third point that we can discuss for comparing the acidity of the phenols and alcohols is that the ions formed after the release of the proton in both cases, like this. In case of alcohols, when the proton is released, then alkoxide ion and hydrogen ion is formed. This way, alkoxide ion and proton is formed. And in case of phenols, when proton is released, we get a phenoxide ion. This is a phenoxide ion. So now we will compare the stability of the ions. So phenoxide ion is more stable as compared to alkoxide ion. So that is why we can say that phenol is more good acid as compared to alcohols. Now why and how is phenoxide ion more stable as compared to alkoxide ion? That we can again tell that in case of alkoxide ion, there is no resonance, so we can see that the negative charge is localized on the oxygen. So localization of charge on a particular atom makes it unstable. But in case of phenoxide ion, this negative charge is not localized on this oxygen only, it is delocalized over the whole benzene ring, as we can show with the help of resonating structures of phenoxide ion also. So I am going to draw the structures of the resonating structures of phenoxide ion, as well as I will also draw the resonating structures of phenol. Then I can compare that phenoxide ion is more stable as compared to phenol also. It is more stable than alkoxide ion also. So that is why we can prove that phenol is better acid as compared to alcohol. So one thing we have discussed, that here it is localized, here it is delocalized. Second thing we will discuss that phenoxide ion is more stable as compared to phenol. So for that I am going to draw the resonating structures of phenol as well as phenoxide ion. So first I will draw the resonating structures of phenol. This is phenol. There are two lone pairs on oxygen. Due to electron withdrawing nature of the benzene ring, this lone pair is attracted towards the benzene ring and this bond will come here. So in the next resonating structures, we will have only one lone pair on oxygen, double bond here, and therefore positive charge on the oxygen. When oxygen is left with one lone pair, positive charge appears. When there are three lone pairs on oxygen, negative charge appears. And when it is having two bond pairs, two lone pairs, then no charge. So here it is left with only one lone pair. One of the lone pairs is involved in the formation of double bond with the ring. So here we can see that negative charge shifts here. Then we can show the transfer of another bond to the para position, means negative charge will come on the para. In the first structure it is at the ortho position. In the next resonating structure we are shifting it to the para position, and negative charge will remain as positive charge will remain as such on the oxygen atom, but the negative charge has come to the para position, and this bond, it will shift here, so it will become like this, and in the next it will come here. This bond will shift at the corner, and the next structure will be like this. and in the last structure this will come here, double bond will go to oxygen back, and we will get 2 lone pairs back on oxygen, no charge on oxygen, single bond with the ring, and this way. So you can see that in case of phenol there is separation of charges. So these are resonating structures 1, 2, 3, 4 and 5. In resonating structure 2, 3 and 4 you can see that there is separation of charges. Positive charge is on oxygen, negative is at the ortho position. Positive on oxygen, negative at the para. Positive on oxygen, negative at the ortho again. And in 5 and 1 there is no separation of charges. So separation of charges also make the structures little bit unstable as compared to phenoxide ion. So now I am going to draw the resonating structure of phenoxide ion, in which oxygen is having 3 lone pairs and negative charge also. So again I am shifting this lone pair to the towards the benzene ring, and one of the bond at ortho position. So I will get 2 lone pairs on oxygen, no charge but double bond with the ring, and negative charge at the ortho position. Then I am shifting this bond, negative charge, to the para and this to the next position, and I will get double bond with the ring, and then negative charge at para, and in the next structure this charge will come here and negative charge will again come to the ortho position. So in the next I will get 2 lone pairs on oxygen, double bond, then negative charge at ortho. Next time double bond will go back to oxygen. Again it is having 3 lone pairs of electrons, single bond with the ring, and so here you can see in phenoxide ion there is negative charge on oxygen atom as well as on the ring also. So there is negative charge on oxygen, then ortho in the next para, then again at ortho, then again on the oxygen. So it is delocalized over the whole of the ring. It is not localized at one point. But in case of alkoxide ions, we discussed that negative charge is localized on oxygen atom. But here it is dispersed. Dispersal of charge makes the structures, resonating structures, more stable. So we can say that phenoxide ion as compared to alkoxide ion is more stable due to resonance. It is more stable as compared to phenol also, because in phenol there is separation of charges, but here it is not. Moreover, in phenol there is positive charge on the highly electronegative oxygen atom, but in case of phenoxide ion, oxygen is having negative charge. So overall we can say that phenol is more acidic as compared to alcohols. We have discussed it under 3 parts, that is comparison of we have discussed the comparison of their hybridization state of the carbon to which hydroxyl is attached, then resonating structure, and one we discussed that there is inductive effect in case of alkyl. Yes, one thing more we can discuss here, that is the comparison of the acidic strength of the 1, 2 and 3 degree alcohols. In case of 1 degree alcohols, you can see one of the R groups is involved in plus I effect in case of 1 degree alcohol, and in case of 2 degree alcohols there are 2 R groups. So plus I effect is more pronounced. Due to plus I effect, the OH bond, it is strengthened more. So here the acidic strength is decreasing in case of 2 degree. But in case of 3 degree alcohols, there are 3 R groups. Plus I effect is more increased, so the acidic strength is decreased more. So we can say, if we have to arrange the alcohols in the order of decreasing acidic strength, we can say that 1 degree are more acidic as compared to 2 degree, which are in turn more acidic as compared to 3 degree alcohols. So now the next reaction that we are going to discuss is esterification reaction. But before that, I would like to discuss one more thing, that is the effect of the electron withdrawing or electron donating groups on the benzene ring of the phenols. How do they affect the acidity of the phenols? So now let us discuss what happens. So effect of electron withdrawing group and electron donating group at ortho and para position in phenols. So this is phenol. If there is electron withdrawing group like nitro NO2 group at ortho or at para, what will happen? It will withdraw the electron density towards itself. So in turn, what will happen? This way it will withdraw electron density towards itself. So what will happen? This will in turn cause the more dispersal of the negative charge. So this will also help in easy release of proton from the phenol, because it is withdrawing the electron density. Then alternative successive bonds, the electron density will be shifted towards the electron withdrawing group, and in turn this bond will become weaker, OH bond. So there will be easy release of the proton and it will increase their acidic character. But in case of electron donating group like methyl group at ortho or para position, it will release the electrons, which in turn will strengthen OH bond. So the release of the proton will become little bit difficult. So then the acidic strength of the phenol will decrease. This is a cresol, comes under that. This is orthocresol. Similarly, in case of paracresol also, the acidity is also less as compared to phenols due to this electron releasing group. But in case of nitrophenol, the group which is present here is electron withdrawing and it is more acidic as compared to simple phenol. So if we have to arrange nitrophenols, cresol and phenol according to the increasing or decreasing order of the acidic strength, we can arrange like this, that the more acidic out of the three are nitrophenols. Nitrophenol is more acidic than phenol, which is in turn more acidic than cresol. So this is the decreasing order of the acidic strength of the phenols. One thing more I want to tell, that if this electron withdrawing or electron donating group is present at meta position, here it is present, then it will have no effect, because during the resonating structures of the phenol, of the phenoxide ion, we saw that the negative density or negative charge, it is dispersed over the ortho and para position and not on the meta. So if the electron withdrawing group is present at meta position, it will not increase or decrease, it will have no effect on the acidic strength of the phenols. So this was all about the acidic strength of the phenols. So now we are doing another reaction of the phenols, that is esterification reaction. Esterification reaction of phenols is its reaction with acyl chlorides or acetic anhydrides. So now let us do the esterification reaction of phenols. Now doing the second reaction, that is esterification reaction of phenols. So this reaction, it takes place in the presence of pyridine when the reaction is carried out with acyl chloride or acetyl chloride. So I am writing the reaction of the phenol with acetyl chloride. This is formula of acetyl chloride. The reaction takes place in the presence of pyridine, which is a mild base. Actually, the product formed during this reaction is acid, like this. When the acetylation is carried out, we get this product. So from here Cl and H from here, HCl is also formed as one of the products. So during this reaction, we see that acid is formed as one of the products, and pyridine, it just causes the neutralization of this acid. Pyridine is a base, it neutralizes this acid, and so therefore pyridine is added during this reaction. So this is acylation. So acylation, esterification reaction, it is also called acylation reaction of phenols. So we introduced here acyl group. So this reaction, you know that acylation reaction can also be carried out with the help of acid anhydrides. So now I am writing the reaction of the phenol with acid anhydride. This is acid anhydride, CH3O, CO twice O. This is acid anhydride. Acetyl anhydride, this is, or you can say that it is acetic anhydride. This is acetic anhydride, not acetyl. And the reaction is carried out in the presence of concentrated sulfuric acid and we will get this product. This product we are getting here, that is the phenyl acetate plus acetic acid is formed here. So again here product is an acid. So this is phenyl acetate. So this was the esterification reaction. Now we can also do the esterification reaction. Yes, one thing more, that this phenyl acetate salt which is formed, it also sometimes undergoes rearrangement, and that is called Fries rearrangement. So I am telling you about the Fries rearrangement. Phenyl acetate formed here. This is phenyl acetate salt formed during the acylation reaction. It undergoes rearrangement in the presence of anhydrous AlCl3. When heated with it, the acyl group, it shifts to the ortho position or para position, and we get this salt, hydroxyl group, and at ortho this acetyl group shifts sometimes to para also. So this is just a rearrangement reaction, and the name is Fries rearrangement reaction. Now acetylation of the orthohydroxybenzoic acid, it also takes place. Orthohydroxybenzoic acid also comes under the category of the phenols. So now let's take orthohydroxybenzoic acid. This is, I have taken orthohydroxy benzoic acid. We are doing its acetylation reaction of the orthohydroxy benzoic acid. When we do the acetylation reaction of this orthohydroxy benzoic acid, which is also named as salicylic acid, we get aspirin. This is also known as salicylic acid, and on its acetylation we will get the product which will be acetyl salicylic acid, and the other name is aspirin. So I am writing here anhydride acetic anhydride, and the reaction in the presence of acidic medium gives us, so there will be acetylation of the hydroxyl group, we will get this product. Carboxylic group will remain as such. So name of this product is acetyl salicylic acid. Or the other name is aspirin. Byproduct is also formed, which is carboxylic acid, that is acetic acid. So this reaction is very important, that is acetylation of the salicylic acid, which gives aspirin. Many times this reaction has also been asked in the board exams also. So now we are doing the reaction of the phenol with zinc dust. Third reaction, that is the reaction with zinc dust. Benzene will be formed here and zinc oxide will be formed. Very easy reaction. That is the reaction with zinc dust. So phenol on reaction with zinc, it will form zinc oxide, and what is left is benzene. So it will be also can be written in, when the conversion is asked how to convert phenol into benzene, then we can do the reaction with the zinc dust also. The reaction takes place on heating. So now we are doing the next reaction, that is the reaction with ammonia. What will be formed? Aniline will be formed with ammonia. Ammonia is basic in nature, it will react with phenol, giving rise to formation of aniline, that is aminobenzene. So this is aniline plus water will be formed here, just like acid base reaction. So salt, that is aniline, amino salt, and water is formed here. The reaction takes place at 573 Kelvin in the presence of ZnCl2 anhydrous, that is zinc chloride. Now the next reaction that we are going to write is Reamer-Tiemann reaction, which is very important reaction of phenols. The phenols, they react with chloroform in the presence of basic medium, that is NaOH or KOH, to give saldehyde. So this is Reamer-Tiemann reaction. Fifth reaction, Reamer-Tiemann reaction. A reaction of phenols with chloroform. Very important reaction, many a times asked in the board exams. phenol, and this is chloroform. Reaction with aqueous NaOH. First addition product will be formed, intermediate will be formed, that is when it reacts with sodium hydroxide and phenol. Sodium phenoxide is formed first. After that chloroform it adds, because you know that phenoxide ion is ortho-para directing. There will be electrophilic substitution of the chlorophyll at ortho position, and we will get this product, that is CHCl2 positive, as an electrophile adds at ortho position. So this is an intermediate which will further break to give the final product, that is an aldehyde will be formed as final product. Now in the next step again, reaction with NaOH gives aldehyde at ortho position, it is introduced, and then reaction with acid will give back hydroxyl group here, because H ions from the medium will replace sodium. So again we'll get the final product, that is salicylaldehyde. It is orthohydroxybenzaldehyde. Orthohydroxybenzaldehyde, or the other name is salicylaldehyde. So this was Riemer-Tiemann reaction, very important reaction. Now we also know that phenols, they also show electrophilic aromatic substitution reactions. Aromatic substitution reaction means the substitution of the benzene ring in phenol takes place. It is not the substitution of the H of the hydroxyl group, but it is the substitution of H from the benzene ring. So it is electrophilic aromatic substitution reactions. So mainly we will do here nitration, halogenation, no doubt sulfonation also takes place. So now let us discuss few electrophilic aromatic substitution reactions of phenols. Electrophilic aromatic substitution. Reactions of phenol. So as you know that hydroxyl group in the phenols is highly activating, it is ortho-para directing, so it will direct the electrophile, incoming electrophile at ortho or para position. So we'll get a mixture of ortho and para products, and the para is always major. So first of all we will discuss the nitration under this electrophilic substitution, aromatic substitution. So nitration, as you know, takes place with nitric acid, dilute nitric acid at 298 Kelvin. So dilute nitric acid at 298 Kelvin introduces NO2 group, that is nitro group is introduced. We get a mixture of orthonitrophenol as well as paranitrophenol, and orthonitrophenol is the minor product, paranitrophenol is the major product. This is due to steric reasons. This is major product. This is orthonitrophenol, this is paranitrophenol. So if we want to separate this mixture of orthonitro and paranitrophenol, we can separate with the help of steam distillation. As in case of orthonitrophenol, we know that there is intermolecular hydrogen bonding. If I show it like this, nitro group like this, there is intermolecular hydrogen bonding here, but intramolecular here, intramolecular hydrogen bonding here, but intermolecular in case of para-nitro. I am showing it again. Intra in the case of ortho, intermolecular hydrogen bonding in the case of para-isomer. This way. So this will be stream volatile, as there is no intermolecular hydrogen bonding. Intra is there. So it will be volatile, this will be left behind. We can separate a mixture of ortho-para-nitrile by steam distillation. Now coming to the reaction with concentrated nitric acid. If the reaction is carried out with concentrated nitric acid, we will get a tri-nitro product which is called picric acid. So how? Let us write the tri-nitro product. This one with concentrated nitric acid, if it is carried out, we get this 2, 4, 6 trinitrophenol. Other name is picric acid. It can also be prepared by treating this phenol first with sulfuric acid. So when we treat it with sulfuric acid at 373 Kelvin, we get a mixture of ortho and para sulfonic acids. Ortho and para, at a ortho and para position, sulfonic acid group is introduced by reaction with sulfuric acid, which is further treated with nitric acid to get the picric acid in good yield. Otherwise, with concentrated nitric acid we can get, but not in good yield. Yield is very poor here. So to get a good yield, we treat it first with sulfuric acid, sulfonic acid here at ortho, as well as this is introduced at para also, SO3H. So we get this mixture, and from this isomeric mixture on treatment with nitric acid, again HNO3 concentrated, we get this picric acid. Now the yield is good. So this was nitration reaction, which comes under electrophilic aromatic substitution. The first that we did was the nitration. Now we will do its halogenation, and halogenation we will do particularly bromination reaction. So now let's coming to halogenation, that is a bromination. So under different conditions, when bromination is carried out, if in the presence of solvents of low polarity like chloroform and CS2, then we get a monobromo product, that is either orthobromo product or para, and we know that para is always the major one. So phenol on treatment with bromine in the presence of low polarity solvent like CS2 or chloroform etc. at 273 Kelvin yields a mixture of orthobromophenol and parabromophenol. This is orthobromophenol, and this is parabromophenol, and the parabromophenol is the major product. This one is the minor. But if the reaction is carried out in the presence of bromine water, then we get a tribromo product, which is white PPT, and is also used as a distinguishing test between the alcohols and phenols. So this was the reaction with, we did that this reaction with bromine in the case of solvent of low polarity, and now we are doing reaction with bromine water. So here we get tribromo product, two, 4, 6. Tribromo phenol is obtained, which is a white PPT. Now we are doing the next reaction that we are going to do is the Kolbe reaction of phenols. So Kolbe reaction is the reaction of phenol with carbon dioxide. Carbon dioxide is a weak electrophile, and we know that when phenol reacts with sodium hydroxide, phenoxide ion is generated, which is highly activating, and it reacts even with the weak electrophiles like CO2. So CO2 adds at, like other electrophiles, it also adds at ortho or para. So at ortho position it is introduced. So let us do now Kolbe reaction. One of the very important reactions of phenols. This is phenol. Reaction of the phenol. The sodium hydroxide generates sodium phenoxide. Highly reactive phenoxide ion reacts with carbon dioxide, and we will get a product like this. CO2 is introduced here at ortho position. Hydrogen is already present here, so CO2 is also here introduced, and we get this product, carboxylic acid at ortho position. And then treatment with H positive ions further gives phenolic group, hydroxyl group here, and carboxylic at ortho position. So it is orthohydroxybenzoic acid or salicylic acid. Or other name is salicylic acid. So the final product of the Kolbe reaction is salicylic acid. Now the last reaction we are going of the phenols is oxidation reaction. Oxidation reaction takes place in the presence of oxidizing agents. The important one is sodium dichromate in the acidic medium, and the product formed is a diketone. The name is benzoquinone. Now let us write the reaction in the acidic medium. This is oxidation reaction of phenols. This is phenol, and this is oxidizing agent, that is sodium dichromate in the presence of sulfuric acid, and the product is a diketone. This and the name is benzoquinone. So this was all about the chemical reactions of the phenols, and you have studied all these reactions in very much elaborated form. I think all the concepts are very clear to you. Thank you for watching a video. Comment it, share it, like it, subscribe it, and also don't forget to press the bell icon to get the latest videos. Thank you.